Okay, these notes are here to help you finish up your homework in section 5.1. I just want to remind you of some formulas. We have these linearity of sums formula here. And it's kind of like, you can kind of think of it as a distributive property, sort of like we did with the derivative 2 on the summation. And then if you have a constant, it just tags along out front. And then when you're adding up the numbers, if you have a sum from 1 to n of k, some constant, like the sum j goes from 1 to n of, say, 7, and we'll say j goes from 1 to 3, then that just means 7 plus 7 plus 7. This is the a sub 1, and then a sub 2, and then a sub 3 term. So that's kind of how you can think of it. As your j is incrementing, it's counting from 1 to 2 to 3. The number is always 7. So the answer to that, of course, is 21. All right, and then we have these cool power sums, and we talked about where those come from, and they're nice little formulas that you're going to have to apply. So let's look at example. This is a few examples. This is number 33 in the exercises from the textbook, and it says find the sum as j goes from 1 to 20 of 8j cubed. So if you just think about that, that's 8 times 1 cubed plus 8 times 2 cubed plus 8 times 3 cubed plus, and you continue in that all the way till you get plus 8 times 20 cubed. So we don't want to do that. That's going to be really tedious. So let's use one of our formulas. You'll see this formula deals with j cubed, and it is that you can think of it as n to the 4th over 4 plus n to the 3rd over 2 plus n to the squared over 4, where the n is the index here, the counting index there, or the high number there. Okay, now this 8 tags along in each one, so that really applies to this theorem right here, or this property, where you can take that 8 out in front and then do the sum. So you can think of this as 8 times the sum as j goes from 1 to 20 of j cubed, which then we can apply the formula number 5 there. It's going to be 8 times n to the 4th, which is 20 to the 4th over 4, plus 20 to the 3rd over 2, plus 20 squared divided by 4. And this you can just type into your calculator. So you're going to do 8 times 20 to the 4th divided by 4 plus 20 to the 3rd divided by 2, plus 20 squared divided by 4. And you get 352,800 as the sum there. Okay, now let's try another problem. Now this one looks scary. Now we want to consider the limit as n goes to infinity of our sum. So we're going to use our properties from before dealing with the limit, and then also our properties that we just learned with our sum power rules. So the first thing that you have to recognize when you're looking at these is that n you're looking at as n goes to infinity. So remember, this number maybe is 10, and then 100, and then 1,000, and then 10,000. So this number is fixed while the I is changing. First you put 1 in, then you put 2 in, then you put 3 in, and you add those all up all the way up to n. So this n cubed is like a constant. It's just that it's a constant going to infinity. So you want to think of this as the limit as n goes to infinity of 1 over n cubed, because we can pull that out. That's going to be the same each time, times the sum of what you have left over, which is I squared minus I plus 1. Okay, now you can use your linearity rules here, the limit as n goes to infinity of 1 over n cubed, so you can sort of distribute the summation. So this is, again, I goes from 1 to n. So this is going to be the summation I goes from 1 to n of I squared, we have a formula for that, minus the sum as I goes from 1 to n of, I need to be consistent always doing capitals, sorry, in another textbook they do lowercase. Okay, so minus I goes from 1 to n of I plus the sum as I goes from 1 to n of 1. All right, So then this is just going to be the limit as n goes to infinity of 1 over n cubed. Okay, we have a formula for the sum of the terms squared. It's a j here, but it's the same thing. So this is the formula we're going to use there. N cubed over 3 plus n squared over 2 plus n over 6. That's what we'll replace this with. So n cubed over 3 plus n squared over 2 plus n over 6. Just applying that formula. All right, and then subtracting the formula for when you're just adding up the numbers. This is like 1 plus 2 plus 3 plus 4. If you look up here, you'll see that formula is n squared over 2 plus n over 2. You have to be careful because you're just going to be subtracting that. So n squared over 2 plus n over 2. And then in your linearity formulas, this means 1 plus 1 plus 1 plus 1 plus 1 n times. So this is just n times 1, just n. Okay, so let's not be too scared by this. Remember, we're taking a limit, so in the end we're going to try and plug it in, because that's what we love to do with limits. So let's see. Notice this minus n squared over 2 kind of cancels right there, right? And you could put these two together if you wanted, but you actually don't have to, and I can go ahead and evaluate the limit. Because for some of these, if n is if the largest value of n is in the denominator, as n goes to infinity, the whole thing is going to collapse down to 0. So let's go ahead and distribute this 1 over n cubed onto each of the terms and see what happens. Okay, so notice here, this is going to be 1 over n cubed times n cubed over 3. So this is n, which is just going to be, and I'll go ahead and show this step. So that's going to be n cubed over n cubed times 3. Plus, all right, now when I do it times this one, it's going to be n over n cubed times 6. And then notice the minus here, minus n over 2n cubed, and then plus n over n cubed. Okay, well, some fun stuff happens here. Notice these n cubes cancel here, so you're going to have 1/3 there. Then you're going to have, this will change to a squared, right, because you'll cancel. And then this will cancel with a squared. And then this will cancel with a squared. So you end up with the limit as n goes to infinity of 1/3 plus 1 over n squared times 6 minus 1 over 2n squared plus 1 over n squared. Now, what do you know about this? Well, as n goes to infinity, this is just going to stay 1/3. But this term is going to go to 0 because the n squared is in the denominator, so that's going to grow really fast and collapse that whole thing to 0. This one's going to 0 also, and this one's going to 0 as well. So this limit is actually 1/3. So that's pretty snazzy. Okay, now looking at what we learned last time, we remember that we have these Riemann sums. I'm gonna look at now the limit of the number of rectangles as I'm sorry, these are not Riemann sums. These are just our summation formulas for the right hand, using the right hand of the interval, using the left hand of the interval, and using the midpoint. Those were our little scary formulas with the summation. Now, it turns out, this is from the textbook, they say figure 10 shows several right endpoint approximations. Notice that the error corresponding to the region above the graph, so this error like they're talking about right in here, gets smaller as the number of rectangles increases. In fact, it appears we can make the error as small as we please by taking the number of rectangles large enough. If so, it makes sense to consider the limit as n goes to infinity. This should give us an exact area under the curve approximation. And in fact, it does. See how you have less and less error the more and more rectangles you put in there. So it turns out by this theorem, if you look at the limit as n goes to infinity of r sub n, or L sub n, or M sub n, they're all going to be equal to the limit, which is the area under that curve. So this is easy to see, and this is going to be, I promise this is kind of painful. So this is not students' favorite thing to do, but I just love it. Just love it, love it, love it. Okay, okay, so now on number 46, we're going to calculate the limit for the given function and an interval and verify our answer with geometry. So you can do this the easy way and the hard way, and we're going to do it both ways. Here is the easy way, geometry, if you remember the formula for the area under a trapezoid, but I think I remember it. Right, this is a line, right, 3x plus 6, but we want to consider the part of the line on the interval from a to b, where a is 1 and b is 4. So if I plug 1 into this equation, I get the coordinate 1, 9. All right, so that's that coordinate. And then if I plug 4 into this equation, I get the coordinate, let's see, that's going to be 12 plus 6, that's 18. So I have this line where you have, this is the coordinate 1, 9, and this is the coordinate 4, 18, and I'm looking at this line right here. So what we want is the area under the curve, between the x-axis and the curve there, that area. We're looking for that area. And we remember this, hopefully, is a trapezoid, and the formula for the area of a trapezoid is equal to 1/2 the sum of the bases, which are the parallel sides, times the height, which is the distance between the bases. So this is your height, and this could be like B2, and this could be B1. All right, and so you can see that B1 is 9 units. So this is 1/2 9 plus B2, which is 18 units, times the height, which is 1, 2, 3, the length of the interval there. So this simplifies then to 9 plus 18, which is 27. So that's 27 halves times 3, and 27 times 3 is, let's see, 81. So this is 81 halves. Okay, about 40.5 is the area under that curve. All right, well, let's see if we can think of it using this idea of the limit with our summation. So this is going to be pretty scary, so everybody take a big breath. Right, here's your formula for r sub n. It's delta x times the sum, j goes from 1 to n, of f of a plus j delta x. And what we want to do is we want to consider the limit as n goes to infinity of that. So let me just write that down. We want the limit as n goes to infinity of r sub n, which means we want the limit as n goes to infinity of what r sub n is, which is delta x times the sum as j goes from 1 to n of f at a plus j delta x. Okay, so that looks scary, but we have an f, okay? We have an a, we have a b. We have a formula to find delta x. Delta x, remember, is equal to b minus a divided by n. Well, your b and your a are 4 minus 1 divided by n. Now, n is going to be going to infinity, so we just leave that. So that's going to be 3 over n. Okay, we also need a plus j delta x. A plus j delta x. Well, that's equal to a, which is 1, plus j is going to be counting, times 3 over n. So that, because that's what delta x is. So this is 1 plus 3j over n. Now this equation, 1 plus 3j over n, is what's going to be plugged in for x in f, because we want f of a plus j delta x. So f of a plus j delta x is going to equal f of 1 plus 3j over n. All right, well, I'm going to put that in for x in f. F is 3x plus 6, so I'm going to do 3 times 1 plus 3j over n plus 6. And if you use distributive property and clean this up, this is going to be 3 plus 9j over n plus 6, which is 9 plus 9j over n. So that is f of a plus j delta x. So you're going to take this whole thing and you're going to pop it in here. All right? And delta x is going to go right in there. And then we're going to take the limit. We're not going to cry. Okay? There's no crying in calculus. Okay, so there's the limit as n goes to infinity of delta x, which is 3 over n, times the sum as j goes from 1 to n of f of a plus j delta x, which is 9 plus 9j over n. Okay? Now, we can use some of our properties to analyze this. The limit as n goes to infinity of 3 over n. First, we can think of this as the summations. We can think of them separately. So the sum as j goes from 1 to n of 9 plus the sum as j goes from 1 to n of 9j over n. Okay, well that's all right. We can think of this as the limit as n goes to infinity of 3 over n. Okay, what's this one? This means 9 plus 9 plus 9 plus 9 plus 9 n times. So this is 9n. That's the formula when you're adding up a constant. Okay, this one, let's think about it for a minute. Remember the 9 over n is just hanging out. Those are just numbers. If we knew what this n was, we would have a number there. So we can bring that out in front and just look at the sum as j goes from 1 to n of j. Well, we have a formula for that. If you come back up here, that formula, the sum as j goes from 1 to n of n, is right here. N squared over 2 plus n over 2. So I can replace this part with what it is in the formula, which is n squared over 2 plus n over 2. So now I'm thinking of the limit as n goes to infinity of 3 over n times 9n, plus 9 over n times the formula, which was n squared over 2 plus n over 2. Okay, now I'm going to evaluate this limit. So let me clean it up a little bit with some algebra, and I'm going to do it in 2 steps. So this is the limit as n goes to infinity of 3 over n. I'll distribute that in a minute. And then 9n plus. Okay, so if I use the distributive property here, 9n squared over n times 2, so the n will cancel with one of those, right? And so I'll have 9n over 2. And then when I use the distributive property here, the n's are going to cancel, and I'm just going to get 9 over 2. Okay, and now I can, in the next step, I'm going to do the distributive property again. I'm going to distribute out this, and then I'll finally be ready to take the limit. So this is the limit as n goes to infinity of 27n over n plus 27 over 2, because see how those n's are going to cancel, and then plus 27 over 2n. All right, well, let's do some work. We're almost ready to evaluate the limit. I should have canceled these n's right away, so it's just 27. So this is going to be the limit as n goes to infinity of 27 plus 27 halves plus 27 over 2n. Well, as n goes to infinity, 27 stays 27, and 27 halves stays 27 halves. But this whole thing is going to collapse to 0. So you're going to get 27 plus 27 halves, which is then equal to, let's see, I hope it's equal to what I got with my area under my trapezoid. Let's see, 27 plus 27 divided by 2, enter, yay, 40.5, which if you math frac that bad boy is 81 halves. So yes, the long way and the easy way if you remember formula. Okay, so and then let's do one that there is no formula for. So maybe, and we will in the next unit, actually in the next section, find a formula for this. Okay, so what we want here is we want to find a formula for r sub n and compute the area under the graph as a limit. So I am going to look for the formula for this problem, and I just want to see, let me check in the back whether they look for a general formula or yeah, they just want the just over this interval. Okay, so here we go. We'll just do it over this interval. So let's just imagine what this is. This is the interval looking for the interval from 0 to 1 of x squared, which is just this parabola. So we're just looking for this area under the curve, and we don't have a geometry formula that we can use for that. So we're going to have to use our scary limit formula. So we want to look at the limit as n goes to infinity of r sub n. Well, that is the limit as n goes to infinity of delta x times the sum as j goes from 1 to n of f of a plus j delta x. That's that formula. All right. Okay, so let's figure out what A is 0, B is 1. All right, so delta x is b minus a over n. So in this case, it's going to be 1 minus 0 over n, or just 1 over n. All right, a plus j delta x, this is nice. Since a is 0, it's going to be 0 plus j times 1 over n. So that's just going to be j over n. So we need to find f at a plus j delta x, which means we're going to need to find f at j over n. Well, f of x is x squared, so this is just going to be j over n squared. So hopefully your little brain is moving very quickly and you're saying, oh yeah, you're going to plug in the formula and do your limit, yada, yada, yada. And you are right. So here we are with our formula. Now I'm going to come in and plug in all the parts that I know. I know delta x is 1 over n, so I'm going to pop that in there. I know f at a plus j delta x is j squared over n, so I'm going to pop that in there. And I'm going to look at this limit and pray that I get the right answer. So this is going to be the limit as n goes to infinity of 1 over n times the sum as j goes from 1 to n of f of a plus j delta x, which is just j over n quantity squared. Okay, well that's just the limit as n goes to infinity of 1 over n times the sum as j goes from 1 to n of j squared over n squared. Now the reason I did that is because this n squared is not changing. Whatever n is, it's always the same. So this is a constant that you can like bring out in front, right? All right, and so we can think of this as the limit as n goes to infinity of 1 over n cubed times the sum as j goes from 1 to n of just j squared. But we know this. We know this sum, or we have a formula for it, right? If we go up here to the top, way up here, we see our formula for j squared is n cubed over 3 plus n squared over 2 plus n over 6. So we will write this as the limit as n goes to infinity of 1 over n cubed times what the formula is for the sum of the things squared, which is n cubed over 3 plus n squared over 2 plus n over 6. All right, just popping in the formula. Okay, and now we're going to hippity-hoppity with the distributive property. Boom, here, here, and here. And you'll get the limit as n goes to infinity. 1 over n cubed times n cubed over 3, those are going to cancel. You're just going to get 1/3 plus, all right, this is going to be an n squared and an n cubed. This is going to be 1 over 2n plus, and then this one, the n and the n cubed, is going to cancel, so this is going to be 1 over 6n squared. And then we're ready to evaluate the limit. As n goes to infinity, 1/3 is just going to stay 1/3, but this is going to go to 0, and this is going to go to 0. So your answer is just 1/3. Yay! And soon you are going to learn that the integral from 0 to 1 of x squared dx is equal to 1/3. But I can't tell you why, but that's what's coming up. So it's very exciting. And to end on this historical perspective, if Bernoulli, who lived from 1654 to 1705, actually came up with a formula for these power sums, which is just really cool. So like if you wanted to know the sum j goes from 1 to n of j to the 4th, you can use his little formula like that and calculate the answer. So that's pretty neat. And like it says, these formulas are available on most computer algebra systems. All right, and so he was, with the help of these formulas, it took me less than half of a quarter of an hour to find that the 10th powers of the first 1,000 numbers being added together will yield this sum. So that'll make you feel bad. Bernoulli was able to add up those numbers in half of a quarter of an hour. Less than half of a quarter of an hour, so in 7 minutes. So you're just a smarty pants, aren't you, Mr. Bernoulli? Okay, see you. Do some homework, guys.